mathematics. He's one of the few people who knows the hard stuff and can explain it to you in a very simple fashion. The last time I introduced him, he just suggested that I leave him 15 minutes for his talk. So I don't want to say that much more, except you're going to be delighted with what you hear.
Thanks, David. So let me say I'm really delighted to be here at this conference. I've been at a number of conferences in Brazil, but this is actually the first time I've had the pleasure to be here at IMPA. So consider the following. I want you to consider the following simple closed curve. So it's a curve on the boundary of a solid cylinder in R3. So it consists of a diameter across the bottom and another diameter across the top, and then you want curves on the sides of the cylinder joining the top to the bottom. And I want those curves to be, each of those two curves to be a helix. Okay, and similarly on the other side. Okay, so it is diameter, two straight line segments, and two helices. Okay, so that's a curve, and for not for everything, but for crucial things to say, it's very important that the top diameter and the bottom diameter not be parallel. Okay, that turns out to be quite important. Let's see. So I say the curve. Let's say the curve winds around about n times. I guess it can't wind around exactly n times, or else they would be parallel. But have it wind around approximately n times, and call that curve gamma n. Okay, so consider a curve like that. And question I want to ask is, how many minimal embedded disks does that curve bound? Okay. So it's just the classical plateau problem for this particular curve. And you might ask, why I'm asking about this curve, these particular curves instead of some other curves. And actually, I was led to consider these curves in trying to understand the very deep theory of Colding-Minicozzi about minimal embedded disks. Somehow that led me naturally to this class of curves. And as I'll explain later in the talk, I think understanding this question for these particular curves gives new insights into the Colding-Minicozzi theory. Okay, so take this curve, what are the minimal embedded disks that it bounds? Okay, well, notice one disk it bounds is a portion of the helicoid. And in fact, that's how this curve was chosen. I just took a helicoid and shrunk it down, intersected with a solid ball. That's that surface there, and the boundary is this curve. So we know one minimal embedded disk that it bounds, the helicoidal surface. Okay, and notice that surface is invariant under 180-degree rotation about the axis z. Okay, that has 180-degree rotational symmetry about the axis. And in fact, it's not too hard to show that helicoid is the only minimal disk that has that symmetry. It's the unique minimal surface with the given boundary and that has 180-degree rotational symmetry about the z-axis. Okay. Now, when n is large, that surface is definitely not area minimizing. Okay, there are various ways to see that. For example, it's clear that as you put more and more winds there, the area of that helicoidal surface will go to infinity. So the area is going to infinity. On the other hand, notice that this curve divides the boundary of the cylinder into two pieces, each of which is a disk. So the area minimizing disk has to have less area than either of those pieces. So, for instance, one piece looks like, what is it, this? has maybe, I don't know, down here. So this, it divides the boundary of the cylinder into two pieces. One piece looks like a half disk on top, a half disk on bottom, and then kind of a ribbon going from top to bottom. Okay. The area minimizing disk has less area than this disk. So that means, so as I say, as n goes to infinity, the area minimizing disk has sort of small area, whereas Hn has huge area. So Hn is definitely not area minimizing. So that means in addition to this surface Hn, there has to be at least one other surface, an area minimizing disk. But in fact, there have to be at least two surfaces, because if you have one area minimizing disk, you can rotate around the z-axis and you get a second one. So remember, the Hn is the only one that has symmetry, so every other surface, any other surfaces occur in pairs. Okay, okay, so we have, oh yeah. So let me mention, so we get this area bound that the least area disk has less area than this surface. And in fact, it's not hard to show that when n is very large, the area minimizing disk is a slight perturbation of this. So it just looks like this, but it sort of bends in a little bit. So it's a slightly curved version of this guy. Okay, so the area minimizing disk actually looks very much like this, one of these two components of the that lies in the boundary. Okay, so now we've seen that gamma n bounds, when n is large, bounds at least three disks, the Hn and two area minimizing disks. Okay, but in fact, it turns out it bounds many more than that. It bounds many embedded minimal disks. So in particular, this surface Hn has some index of instability. We don't know exactly what it is. But one can prove that gamma n has to have disks of index, well, 0, the minimizer, but it also has to have disks of index 1, 2, 3, etc., all the way up to the index of h of n. Maybe it has ones of bigger index too, I don't know, but at least it has each of those indices. And of course, each one of those, has to occur in pairs. Okay. And furthermore, it's not too hard to show that the index of this Hn is roughly n. Okay, or at least it's at least n. I don't know. Maybe it's much bigger than that. I'm not sure, but it's fairly easy to bound it below by n. Okay, so in other words, so the number of minimal embedded disks grows at least like 2 times n. Okay, so there are lots and lots of minimal embedded disks with this boundary. Okay, in fact, I think it grows much faster than that. So I would conjecture that the number of minimal embedded disks grows at least like 2 to the n. Okay, so I have a kind of heuristic argument for why that should be true, but I think it's would be quite a challenge to prove that. I think it's quite an interesting problem to try to prove a bound like that. Okay, so we see when n is large, this bounds lots and lots of minimal embedded disks. So can we understand anything about what these disks look like? What do these minimal embedded disks look like? And I have a sort of a partial answer to that question. I know something about what they look like. So consider a minimal embedded disk with that boundary where n is very large. And then a very surprising thing happens. Turns out either that disk is very similar to a helicoid or it's very different from a helicoid. It can't be sort of like a helicoid. Very helicoid is either very much like a helicoid or totally different from a helicoid. Okay, so let me make those that statement precise. So by similar to a helicoid, I mean that it's nearly horizontal away from the z-axis. So here's a helicoid, and then one when we've shrunk it down more. So here the number of turns is 4. They're at 16. And so here you can see that, well, of course, it's exactly vertical along the z-axis. But if you go a little bit away from the z-axis, then if you go a little bit away from the z-axis, it's almost completely horizontal. So that's what I mean similar to a helicoid. Similar to a helicoid means it's nearly horizontal if you're away from the z-axis. Okay, so let me introduce a little notation. So if M is a surface in R3, let me say slope M is the supremum of the slopes of the tangent planes. Okay, and Z of R means the solid cylinder of radius R about the z-axis. Okay, so if you take this helicoidal surface, the slope is infinity because it has points where the slope is where the tangent plane is vertical. So if there's any place where the tangent plane is vertical, slope is infinity. Even though, of course, there are lots of places where the slope is small. If there's any place where it's vertical, the slope is infinity. So this slope is infinity. But if you remove a little cylinder around the z-axis, then what's left has very small slope. So cut out the cylinder, let n go to infinity, the slope will go to 0. Okay, so now let me state a version of the dichotomy theorem. So I guess I didn't say this, but I always want to think of this cylinder as having radius 1, say, and height 1. Okay, so this is radius 1 and height 1. And so pick some r between 0 and 1, and take a sequence of these disks with dn is a disk with gamma n, and I'm going to let n go to infinity. And then after I pass a subsequence, one of two things can happen. One thing is that outside of this smaller cylinder, the slopes are going to 0, just like they do for the helicoid. That's one possibility. So in this talk, I'm thinking of the helicoid as good, so that's good behavior. It's behaving like a helicoid. That's one possibility. Either that slope goes to 0, like the helicoid, or it goes to infinity. Okay, it can't go to any finite value. Okay, so in that sense, 0, it's very like helicoid, or infinity, that's extremely different from the helicoid. Okay, but it's impossible for that to have a finite positive limit. But let me sort of restate it in maybe a more striking way. So now I want to let me draw the cross section of it. So I take a very small radius epsilon, and then another radius which is very nearly equal to 1. Okay, so epsilon, you have 0 less than epsilon less than r less than 1, but think of epsilon as being very close to 0 and r as being very close to 1. And now again, take dn as embedded minimal disk with boundary gamma n. We want to let n go to infinity. Then the theorem says if when you're very near the outer boundary of the cylinder, if the slope is bounded out there, so C can be huge. So in this little region here, in this region very near the outside of the cylinder, if you just have any bound on the slope there, then you have if you have a little bit of control out at the boundary, then you have extremely good control, all the way until epsilon. The slopes are bounded out near the edge of the cylinder, then they're almost 0 until you get very, very close to the boundary. Okay, and so here, this constant, let me emphasize, can be extremely large. So you just need any extremely weak control out here, gives you extremely good control all the way until you're practically at the z-axis. And this generalizes in various ways. One is, for this theorem, it's not important that these curves actually be helical. Okay? All that you need is that the slopes go to 0. So you're getting, again, the slope means soup of the slope, so that as n goes to infinity, these curves should be getting more and more horizontal. And of course, that means that forces them to wind around more and more times. Okay. So it don't have to be helices. And let me remark that the theorem becomes false if, it's interesting, I said it's important that the upper and lower diameter are not parallel. If the upper and lower diameter are parallel, this theorem, at least for these general curves, is false. And also, the Riemannian metric doesn't have to be the Euclidean metric. Okay? All we need is that for each of the horizontal disks to be minimal. We need two things. Each of the horizontal disks should be minimal with respect to the metric, the Riemannian metric. And let's see, we need the z-axis to be perpendicular to each of those disks. Okay? So those are two things you need. Okay? But modulo of that, it can be any Riemannian metric, not just the Euclidean metric. Okay. Actually, of course, if you take for an arbitrary Riemannian metric, it doesn't really make sense to talk about the top and bottom being parallel. That doesn't make any sense. So that condition you have to sort of restate in a slightly different way. Okay, but now, so if you talk about a general curve or a general Riemannian metric, then so the dichotomy theorem is true. The minimal embedded disks divide up into these two extremely different classes, but it's not clear those classes are non-empty. So if you take a general metric, then you could ask, well, do we know that the good disks and the bad disks both exist when n is large? And for bad disks, yes, they definitely exist. For instance, the area minimizing disk is definitely bad. Okay, and that's easy to see because a disk that is good, that meets our definition of being good disk, it's nearly horizontal away from the axis. Again, such a disk, its area goes to infinity as n goes to infinity. Whereas the area minimizing disk has a bounded area. Okay? So the area when n is large, the area minimizing disk will definitely be bad. So they're, for whatever the metric is. So they're definitely, bad disks definitely exist when n is large. Okay, what about good disks? Well, it turns out when n is large, good disks also exist. So when n is large, it's easy to see there are going to be some minimal embedded disks that are not like the helicoid. But how do we know that when n is large, there has to exist a minimal disk that is like the helicoid? Okay? So the answer is yes, but that's much more subtle. Okay, so the existence is given by this theorem. So fix a small epsilon. So that's the level. It reflects the level of goodness that we require. And the theorem says that for all sufficiently large n, there exists a minimal disk with the given boundary, with boundary gamma n, such that the slope, if you go epsilon away from the z-axis, the slope is less than epsilon. Okay, so let's we'll call a disk that satisfies that inequality. We'll think of that as being a good disk. Okay. Okay. And so the theorem says that, yeah, if you fix an epsilon, then once n is large enough, there definitely does exist a disk that's good in this sense. Okay, and furthermore, it says d sub n. It should just be d, sorry. There's no, that subscript shouldn't be there. It's just d. But so once n is large enough, there exists such a disk. And in fact, the number of disks is odd. The number of good disks is odd. And here I say properly counted. It's a little bit like when you say the, if you take a degree n polynomial with a generic degree n polynomial have exactly n complex roots. But you can also say any polynomial has n roots if you count roots with multiplicity. So likewise here, if you count disks the right way, then then the number is odd if you count them with multiplicity. But in any case, it's definitely non-zero. Oops. And the proof of this is by the continuity method, which in minimal surface theory is pioneered by Tomi and Tromba. And so here's the idea. So first of all, if you start in the original situation I described, where with the Euclidean metric and these guys are exactly helices, then we know it's true. It's definitely true in that case because it bounds the helicoid itself. So and that's definitely a good surface. And it may bound some other good surfaces too, but remember those occur in pairs. So the number of good surfaces in that case is clearly odd. Okay, so it's true if you start with the Euclidean metric and curves that are exactly helical. And now the idea is to start with that and now deform the metric and the curve. So start with that situation, and now modify the metric and the curve, deform them until you get the configuration that you want. Okay? So you start with the configuration, the standard configuration, you know the answer is true there, and now you deform it and you try to show that it remains true as you deform it. Now if you take, say, a curve, like a curve in R3, and bound some minimal disks, and you start deforming the curve, then the number of disks it bounds can change as you vary the curve. And the reason is that as you're following along, what can happen is, this curve might bound two separate minimal surfaces that come together and then cancel each other out, and you go on, or you take a curve and suddenly you have sort of pair annihilation or pair creation. As you're deforming it, suddenly a disk appears where there wasn't one before, and you deform it a little more, and it splits into two. Okay? So that's the way the number can change as you deform the metric or the curve. Notice in that process, though, that the oddness or evenness is preserved, because either two come together and cancel out, or two get created. So if you start with an odd number and then you deform it, you'll end with an odd number. Okay, however, that's very, very general. But in this case, so it's sort of easy and standard by the continuity method to say that this curve gamma n bounds an odd number of minimal embedded disks. Okay, but we're not just saying it bounds an odd number of minimal disks. We're saying it bounds an odd number of good minimal disks. Okay? So how do you do that? Well, okay, so we don't know. It's not enough to show the oddness of the total number of disks is preserved. We have to show the oddness of the set of good minimal disks is preserved. Okay, but that's okay because by the dichotomy theorem. Because we start off with we have these good disks, these helicoid-like things, and we have the bad ones. And now we modify the metric and sort of follow these along. And we might have some pairs coming together and canceling out or whatever. But notice by the dichotomy theorem, these good ones and the bad ones are far away from each other. So you can never have a good one canceling with a bad one. So consequently, if you just look at the number of good ones, that number has to stay odd as well as the total number. Okay, so this is sort of standard continuity method plus the dichotomy theorem. Okay, so what does it say about the Colding-Minicozzi theory? Well, let me tell you the part of Colding-Minicozzi theory relevant to this talk. So let's take any sequence of properly embedded minimal disks in an open subset of R3, or more generally, an open subset of a Riemannian 3 manifold. And you have to have some mild hypotheses on U. Let me not bother to state what those are. But in particular, oops. Sorry. Yeah. need some mild hypotheses on U. But for instance, any convex open set, in R3, any convex open set would work. Okay, so take a sequence of properly embedded middle disks in an open subset, an open set. And now, the following is a very easy fact. Maybe it was first stated by Colding-Minicozzi, but this is quite easy. That after you pass through a subsequence, there's a relatively closed subset of U, such that the curvatures blow up on that subset. But away from the subset, the surfaces converge smoothly to a minimal lamination. Okay? So you have the U, and you have this closed set, and the surfaces are getting really bad near the closed set. That means for each point in this blow-up set, if you take a point in the blow-up set, there's a point in the disk such that Pn goes to P, and such that the curvature of the disk at the point Pn is going to infinity. So the curvature blows up on this set K, but away from K, it's very well behaved. It converges to a smooth minimal lamination. And lamination, incidentally, is just like a foliation, except it can have some gaps. So if you take a foliation, and then you just take a closed subset of those leaves, I mean, that would be an example of a lamination. So lamination is a foliation, but with gaps. So that's what you get. A closed subset where the curvature blows up, and everywhere else it converges smoothly to a minimal lamination. So let's say that's a very easy fact. Now you can ask, well, what kinds of closed sets K and laminations L are possible? What kinds of closed sets and laminations do you get in this process from a sequence of minimal embedded disks? And before Colding-Minicozzi's work, I think absolutely zero was known about that. I mean, I think it's true that not a single thing was known. Maybe some of the experts can correct me, but so in particular, as far as I know, there was no restriction on the closed set known. For all we knew, it could any closed set. So in particular, for all we knew, the closed set could be all of U. Maybe you could have a sequence of minimal embedded disks where the curvature blew up at every single point. Okay, we just knew nothing about it. But then Colding-Minicozzi proved this amazing theorem. They said in that situation, the curvature blow-up set, so a priori, all you know is it's a relatively closed set. But they proved the curvature blow-up set is contained in a C1 curve. Okay, so it's not just an arbitrary set, but it has to be, a subset, a closed subset of a C1 curve, not necessarily connected curve, but a closed subset of a C1 curve. And they say some other things too. Furthermore, for each point in that closed subset, there's, corresponding to each point where the curvature blows up, there's a leaf of the lamination, which is a punctured disk. It's a minimal disk, a properly embedded minimal disk that is punctured exactly. So here's a point P in K, and then associated to it, there's a unique punctured disk where the puncture is that point. Okay? So there's one leaf which is a punctured disk, and furthermore, the disk is perpendicular to the curve at that point. Okay, and now, so in general, this K might just be a subset of the curve, but of course, it's in some cases, it turns out that K is the whole curve. So it could happen that K is the entire curve. And notice in that case, these disks, these punctured disks actually form a foliation. In that case, okay. Now, so that's basically a theorem of part of Colding-Minicozzi theory. Actually, what I've stated here is a little bit more than what they actually proved. So this statement here is what they proved plus some refinements by Bill Meeks, by myself, and then by Bernstein, Tenalia. So for instance, let's see, they, I guess their work wouldn't tell you C1 curve, it would just tell you rectifiable curve. and you wouldn't get that this is a right angle, but rather just, that there's some lower bound on the angle. And also like that leaf D sub P, from their work you wouldn't know it's a punctured disk. Maybe it could be something like a punctured annulus or a punctured surface of more complicated topology. But anyway, with those refinements, it's so to say, this statement is their theorem plus some later refinements of it. Okay. So now the existence theorem I mentioned gives us what you might call a partial converse to their theorem. So let's suppose so here we start with a sequence of disks, and then you pass a subsequence, you get a curvature blow-up set and a lamination, and you get a picture like this or like this. But now let's start the other round. Let's say we start with let's take the case of a foliation, not a lamination. Suppose you start with a foliation by minimal disks and a curve that meets all those disks orthogonally. Okay? So as I say, that configuration is consistent with the picture that Colding-Minicozzi described. And now existence theorem implies that, in fact, there's a sequence of minimal embedded disks for which the curvature blow-up set is exactly that curve, and the limit lamination is exactly that foliation. Okay. So in other words, any picture which is consistent with what they describe when the limit is a foliation actually does occur. So you can't say any more about that than what they already said. And let me mention, this is a generalization of work of Meeks and Weber. Their method was completely different, but they proved this result if you're working in Euclidean space and if the foliation is a foliation by flat disks. So you start with say a smooth curve, and then you take the disks that are perpendicular to it, the flat disks that are perpendicular to it, and choose the radius that is small enough they don't intersect, so they'll foliate some neighborhood, some tubular neighborhood of the curve. So if you have a foliation like that, that's already in the work of Bill and Matthias Weber from a few years ago. But the method is completely different from the method I've described here. Okay. So what's the idea of the proof? So this is I've just restated the theorem here. So you have a sequence of disks in this cylinder. The slopes way out at the boundary are controlled. And then the claim is the slopes have to be going to zero, if you're just a little bit away from the z-axis. Okay, so we want to prove that. So let me describe the idea of the proof. So first of all, by Schwartz reflection, remember at the top we have a diameter, at the bottom we have a diameter. So then we can reflect to get a bigger minimal surface, and you repeatedly reflect and you get a cylinder, a minimal surface in the entire cylinder. Now actually that's cheating because it doesn't work for general metrics. Okay, so I'm going to cheat because it's already interesting, even in the case of Euclidean metric. But it's not so bad because what it means in general, you just need you need some argument to look at what's happening at the top and the bottom. But by this cheat, then I don't have to talk about the top and bottom. They're not there. So, okay. So by passing to a subsequence, we get a curvature blow-up set K and a limit lamination L. And again, let me draw sort of the cross section. So now it's a whole infinite cylinder. And notice, remember, we have slope bounds near the boundary of the cylinder. Okay? So consequently, the slope bound gives very nice convergence near the boundary. So we know we know it's converging nicely to something like this. We get very nice convergence out near the boundary of the cylinder, and we don't know so much in between. Okay, so yeah, maybe we should mention. So notice these helical curves, when you let n go to infinity, these helices are converging to the foliation of the boundary by horizontal circles. Okay, so that means these surfaces here, I don't know exactly what they are, but the boundaries of those are exactly horizontal circles. Okay, so out near the boundary, I have this nice lamination, and the boundary is exactly horizontal circles. Okay, now, by general Colding-Minicozzi theorem, or Colding-Minicozzi plus some refinements of Bernstein and Tenaglia, you can say that almost every leaf is one of the following things. It's either a properly embedded disk, or it's a punctured disk, as I mentioned before, or it's an annulus. Okay. It's kind of weird, I think, if you're familiar with minimal surface theory, it's kind of weird that it might be an annulus, because usually in this business, when you take a sequence of surfaces and you pass to some limit, usually the limit can have simpler topology, but it can have more complicated topology. Okay, so you take a sequence of genus 1 things, maybe the handle shrinks down and disappears in the limit, so you get something that's genus 0. We're very used to that kind of thing, but usually it's very easy to rule out the other thing, that that you have a sequence of disks, somehow it can't converge to something that has a handle, for example. Most of the time in geometric analysis, it's very easy to rule that out. But in this case, it turns out it's not. In fact, David and I have examples where, in the Colding-Minicozzi setting, where you have a sequence of properly embedded disks, and they converge to a limit lamination, and that limit lamination, even when you don't have any curvature blow up, that limit lamination can include an annulus. So this is one bizarre case where the topology can get more complicated. But Bernstein and Tenaglia proved that you couldn't have anything worse than that. Okay, so you might see an annulus, you might see a punctured disk, but you're not going to see anything genus 1 or higher. So these are the only 3 possibilities you'll see. Okay? And in this particular setting, I say in general, annuli really can happen by these examples that David and I made. But in this particular setting, it turns out it's pretty easy to rule out annuli. Let me not describe that part of the argument, but that's pretty easy. So let's consider a leaf that's either a disk or a punctured disk. So its boundary, remember, is going to be a horizontal circle, and it's either a disk or it might be, a punctured disk. Okay, but its boundary is a horizontal circle, and now by the maximum principle, it has to be a horizontal disk. Because remember, all these horizontal disks are minimal. So if you look at this disk, look at the highest point on it. Well, here you have this horizontal disk was minimal, and this disk is minimal. If they weren't the same, that would violate the strong maximum principle. So in fact, all these so-called good disks, or this, I said almost every disk. Technically, almost every here means anything that's a limit leaf of the lamination. If you take a leaf in the lamination, it's the limit of other leaves in the lamination. It has to be, of type 1, 2, or 3 here. Those limit leaves, this argument shows they have to be horizontal disks. And it's also easy to show that every horizontal circle has to be the boundary of at least one limit leaf. So consequently, the lamination is just the foliation by, the lamination L has to be the foliation by horizontal disks. And now, the blow-up set has to be a curve that meets all those disks orthogonally. Well, again, let's say we're in the Euclidean setting, so that means it's a vertical line. Right? So the curvature blow-up set is, the lamination is all the horizontal disks. The curvature blow-up set is a vertical line. In the Euclidean case, let's just talk about that. So the only thing we have to show is it's actually the z-axis and not some other vertical line. Okay, but this curve, this straight line K has to pass through the curve at the top and bottom, those two diameters. Okay. Now that, by the way, the fact that it has to pass through the curve at the top and the bottom is an easy consequence of a very hard theorem. So it's kind of intuitive, I think, that it should go through those points. But to prove that it does, it's an immediate consequence of this hard fact. And the hard fact is the Colding-Minicozzi one-sided curvature estimate. Okay, the curvature, that's a very hard theorem, but it immediately implies this. So it's a vertical line, has to pass through the top and bottom diameter. And this is exactly where you use the fact that the diameters are not parallel. There's only, the z-axis is the only vertical line that passes through both those diameters. Okay, so that's the proof of the dichotomy theorem. And let me talk about one other thing you can get from the dichotomy theorem, or from the existence theorem and the dichotomy theorem. So here we get these examples where you have an arbitrary curve. So what about, so in particular, like I can take any smooth curve and find a sequence of smooth embedded curve, find a sequence of embedded disks and make that curve be exactly the curvature blow-up set. Okay, that also follows from the earlier work of Bill and Matthias that I mentioned. Okay, so the curvature blow-up set can be any smooth curve you like. But suppose I want the curvature not to blow up on the whole C1 curve, but I take a curve and I pick a closed subset and I want it to blow up on that closed subset. Okay. So again, let's say we start with a. Oh, by the way, let me make a remark. Maybe I should just to say that this is very non-vacuous. It's easy to make lots of examples of open sets foliated by minimal disks. So for instance, you could take any minimal surface you like. One thing you could do is you could take any smooth curve you like and say an R3. Take any minimal surface you like and take a small piece of it. Take a small piece and then put that piece, or let's start with your minimal surface. Take a small piece of your favorite minimal surface and take any smooth curve that meets it orthogonally. And now what you can do is you can just move the surface along, keeping it orthogonal to the curve. So that's one way you can get, lots and lots of examples in R3 of curves and foliations that satisfy this thing. But you can also do this sort of thing in Riemannian manifolds. So take, for instance, a curve, take the area minimizing disk. That's going to be stable. It might not be strictly stable, but if you bring in the boundary a little bit, it's strictly stable. And anytime you have a strictly stable surface, it's easy to prove by the implicit function theorem it's part of a foliation. So if you take a strictly stable surface, then there'll be a whole foliation nearby by strictly stable things. So it's easy to make lots of minimal foliations by disks, and then you take a curve perpendicular to all of them. So it's sort of easy to make situations where this situation applies. But now take one of those. Take a foliation, and take a foliation, take a curve perpendicular to it, but now pick a subset, like maybe a Cantor set. And we can ask, now I don't want the curvature to blow up on the whole curve, I want it just to blow up on that subset. So suppose K is a relatively closed subset of the curve, like maybe a Cantor set, and you can ask, does that closed set occur as a blow-up set? So a few years ago, David Hoffman and I showed that if you're in the Euclidean case with flat horizontal disks, then the answer is yes. So if you take any closed subset of the z-axis, you can find a sequence of minimal embedded disks where the curvature blow-up set is exactly that set. Okay. Now for curves, we can do something, but not quite as much. So the new result, which again follows from the existence theorem, says the following. So take some very small delta, and it says, so this theorem says we don't know if we can get exactly that closed set, but we can get something very close to it. Namely, it says there exists a sequence of minimal embedded disks whose curvature blow-up set is K prime. Oops, this should say where, that should be where K prime is obtained from K by moving each point in K in its leaf by some small distance delta. Actually, yeah. So I've picked this Cantor set, and I'd like it to the curvature blow up exactly at this point, but I don't know if I can do that. But if you allow me to move each of these points a little bit, then in its leaf, then I can make the curvature blow-up set be exactly that set. Okay. Or I think maybe a better way of saying it is so take this foliation and take the curve, and I'd like the curvature blow-up set to be a certain subset of that curve, and let me specify which subset by marking some of these leaves, the corresponding leaves. So I pick a closed subset of leaves. So I pick a certain closed subset of leaves, and then I would like the curvature blow-up set to be this curve intersected with all those selected leaves. That's what I would like to do. And I don't know how to do that. But what the theorem says is if you allow me to perturb this curve a little bit, then I can make the curvature blow-up set be exactly where that perturbed curve intersects those leaves. So I can't get exactly the Cantor set I want, but I can get a Cantor set that's very, very close to it. Okay, so I'll stop there. Thanks.